I want to give you a sneak preview of the kind of TinyML applications that we will be dealing with. We want to understand how to start with sensor data from acoustic sensors, image sensors, and motion sensors, and then train the networks and then evaluate them, right? Each one of these sensors generally fits into one of these application buckets for TinyML that people are envisioning. Let's start with the home scenario. Then we'll work into the office and industrial applications. In the home, the most common one of these is what we call keyword spotting. Now, we've spoken about this many times. Sometimes we even refer to this as hot word detection. You will now build the application from speech input all the way to meaningful response. You will capture the input from the microphone, which results in an audio snippet. The fun part is that you will do this with your own voice data set too, and then convert it to a format that you can feed into a neural network. So the network is able to make an intelligent decision eventually. Specifically in the context of keyword spotting, it's about understanding if you actually said the word that corresponds to the machine. Did I say, hey Siri, or did I say, hey serious, right? It's about detecting that keyword, and that might seem like a very simple thing, but there are a lot of nuances in that because the machine has to be able to pick up the keyword in transient streaming audio. There could be background sounds, it could be overlapping words, there could be loud audience sound around you. Finally, there's the aspect of generating the output, which is in the case of the Alexa example was to simply dim the lights. Now, this is the full end-to-end pipeline. So let me step through the details of this process. The first question is, how do you capture the data to feed into the network? Sure, you're using a microphone, but remember, you have to train the network, right? So you have to understand how you're actually going to be able to get that data that's from the microphone, converted to a signal that the network would actually be able to understand. Should we input it as a streaming audio time series signal or figure out a way to flatten it for more efficient processing? Then there's, of course, a question about how do you design the neural network itself to take in the speech signal? Well, what are the input vectors looking like, right? Then you've got to think about, well, the data set that you're using to train this network, what does that look like? Is it just some kind of arbitrary set of sounds? Let's say, for instance, let's use example, okay, Google. So when I'm doing that, think about what's involved. Okay, Google. Yeah, that's me saying it. How do you say it? How does your mother say it? Well, my mom says it very differently. Sometimes, in fact, the machine cannot pick up my mom's way of saying, okay, Google, because she has a strong Indian accent, which the machine just doesn't understand. But why is that the network does not understand it? Well, it's because the data set that was used in order to train that OK Google neural network model was not fully broad or diverse. And that's a big problem. So we need to understand how the data set is actually constructed. And then we are actually going to be doing something of that in this particular course. And then how do you pre-process the data that's going into that network? So let's say you have this ideal data set that you're now using, and then you have to pre-process it to extract all the key features. You have to do the feature engineering in terms of the training data set, as well as the actual input signal that's coming in. So we'll look into those pre-processing steps. And then, of course, you have to take that output that's coming out of the network. It's not that the network simply saying, oh, it's a cat or a dog. You actually have to do something intelligent. So post-processing that to be able to make the signal that's coming out of the neural network to be useful in the bigger context of this application. You have to take care of the tiny model that you have so that it's not biased. In other words, that it would actually work for me and actually work for my mother as well. So you have to understand how to identify and quantify this bias in the data set before you ship it out into the real world. And of course, there's the ultimate question of how do you deploy this into the tiny little microcontroller? Deploying a tiny little model onto a microcontroller is not simply taking the model you have trained in Google Colab and then simply tossing it onto the microcontroller. There are actually several steps involved in terms of converting the model from a format that it is in to whatever training format that you have trained it at into the deploying environment. And we'll talk about this much more in part 3. In this particular part, I'm going to try and give you some basic guidance as to what's involved, and so that we work ourselves towards that. Similarly, let's look at a different sensor that is in the context of an office environment. In the office context, we're going to be using a camera sensor that is detecting occupancy in a given office building. So if there's no one in that office building room, it should automatically activate the system in order to turn off the lights so that we can conserve energy. That's a very popular use of a TinyML application with vision sensors. There are many others, of course, but that's the one that we are actually really interested in now. So what does that actually involve? We're going to feed camera pixels data into the network. And we want to be able to do is pick up something interesting, like say as person detection, where we are trying to detect the person in that particular image. Of course, this goes back to something you have already done in part 1. You may have trained a convolutional neural network in order to be able to pick up a person and put a bounding box on top of them. What we are going to specifically focus on is with a twist in this part, is how do you accelerate the training time so you can actually then speed up the time to deployment from collecting data to actually getting onto an inference. So we're going to touch on these things called transfer learning, for instance, where you're actually going to learn how to train the network differently and then deploy it much earlier. So you don't have to wait for 2 days for the network to train. We'll just wait a couple of minutes and you're kind of done. But of course, the whole thing comes down to is even if you come up with ways to train the model faster, the ultimate question is how do you shrink this model down? We'll learn about these techniques to prune and compress the network. Some of the nuances that we're going to learn about here are what are the computing operations that we're actually using. For example, can we perhaps change them out so that we can actually do it much more effectively or more energy efficiently? We'll learn about some of the numerical representations and go from using, say, floating point to integer 8 or int 8. If we do that quantization process, then what are the trade-offs that we make over here in terms of accuracy, in terms of speed, in terms of memory footprint? And then how do we prune these networks, by trimming neurons or by removing connections? So we'll go into pretty in-depth into that as different approaches for squeezing these networks and their inference time. We will always focus on this end-to-end flow from collecting your data all the way to training your model and being able to do inferences with it. There are 2 more questions that we will have as we deploy these systems in the wild. How do you ensure that the network that we have trained is actually resilient for different environmental conditions, such as lighting conditions, clutter, or the number of people, for instance, in that office environment? And then how do you make it stronger and more robust and more generalizable so that it can go from one office building to another and maybe to a warehouse, for example? The third application that we're going to be touching on is something that you will find often in industry applications. It's extremely important to understand this use case because people are saying it's going to be the most pervasive. TinyML has huge amount of industry applications. And we're going to focus specifically on the gyroscopes and accelerometers as the sensors here. And we're going to use that for preventive maintenance in vibration systems, such as motors, engines, and turbines, where there's a lot of wear and tear. So this little square that you see up on the top left is an accelerometer, which detects changes in motion or vibration. But the key idea here is that we want to be listening to the characteristics of how this machine is performing in the field so that we can do predictive maintenance. We want to be able to predict if the machine is going to fail in the near future. Why? Well, if we can predict, then downtime goes down, right? For example, in the auto industry, downtime, that's basically when the factory floor has to stop for some reason, can cost up to $50,000 per minute, which equals $3 million per hour. If their neural network was to be able to say, hey, I think this machine is vibrating a little different than normally, then we would, well, that's important because it would raise a flag to the operator who can then send someone out to quickly see if the machine is going to break. And if it looks like that something is actually wrong, they can replace it right away. So and do that without actually having the whole factory plant to stop working. which would prevent them from shutting down the industrial plant and its consequences. So predictive maintenance is seen as something that is extremely valuable, and it really comes down to being able to do all of this sensing in real time, because you have so many different engineering parts that are out there. So we'll look much deeper into this. And what's specifically interesting about this particular application from your perspective is that we'll actually be looking at time series data. Time series data is where you have a continuous signal that's constantly coming through. And when the machine is working normally, like the blue or green lines over here that you're looking at different times, you'll see that the machine is, say, humming initially. And let's assume that the amplitude here is just how the machine is vibrating. And it seems to be going on just fine at this point in time. And the neural network looks at the signal, and then it gives it a thumbs up and says, well, everything is okay. And if everything's okay, well, nothing needs to be done. Okay. But occasionally you might see that the machine is actually having a blip or grinding sound or larger vibrations. Something about the way that it's vibrating, for instance, is off. And then somehow the neural network can pick that up and say, hey, this is abnormal behavior. So let's take a look at it. And how would this network do it? The type of data is actually not supervised learning. When you're dealing with image data, for example, it's supervised learning because you've given it a set of data. You've asked for and then you've asked to find similar kind of features in any new data that's given to you. So if you train on a whole bunch of cats and I give you a picture of what looks like a cat, then okay, well, it's got all these features, so it's probably a cat. Well, that's how you train a neural network in supervised learning. But here, you don't know what you don't know. You've not seen an anomalous signal so far. You're looking for this abnormality, which is not going to be common as a common case when you're looking to train on machines. So it's basically abnormal or out of activity behavior or rare scenarios, and you can't essentially find them easily to train on. So you're looking for something that's a departure from what you've actually trained on in the terms of supervised learning. So how do you get the neural network to actually learn this? Well, that's the really fun thing about this scenario. It's a fundamentally different concept. We're going to introduce this notion as what's called an autoencoder. An autoencoder is quite different in the way it behaves. And we can learn about that when we get to the anomaly detection application. We learn about also how do you design the autoencoder neural network, and how is this autoencoder different from other kinds of networks? So we are trying to cover not only different scenarios of sensors, but different ways to execute across the machine learning pipeline. And that's the really fun part about learning TinyML in this particular course. So that hopefully gives you, a very practical take on machine learning applications, and it's just a preview of what's coming up. So stay tuned.